Welcome guys, welcome to my channel. So today's topic is acid base concepts in biology. So the idea of this video is to oversimplify the concept of acid and base in biology. So let's begin. We all know that the water is the most important component in our living system. Also, it is most important component in a biochemical reaction. In general, this water ionizes into H plus and OH minus, which is also similarly expressed as H3O, where we have a plus sign on an H and OH minus as a dissociation. If you recall your chemistry, you can see that uh, if there is a reaction, say A plus B is in equilibrium with C plus D, we can express it in terms of an equilibrium constant, which is this one, the K equilibrium. What does it mean is the concentration of C D is equal to the concentration of A and B, and so this whole system is in equilibrium. So this concept of ionization, we can put it for water too, where H plus and OH minus is in equilibrium with H2O. Okay, so what does this equilibrium constant mean? This tells us that the amount of water is equal to the amount of H plus and OH minus. If I ask you what is the molarity of a pure water, the molarity of a pure water would be a liter divided by its molecular weight, which comes to 55.5 molar. So 55.5 molar is the molarity of water. So can I write this concentration of H2O, because this is what we are considering is a pure water, so I can write down that it is 55.5 molar. Now any solution or any liquid molarity we find out in the same way. So consider it as a liter of solution divided by its molecular weight. Okay, like for example, if you want to find out for HCl, it would be molecular weight of HCl, and what else? The specific gravity, which in case of water is 1, right? And the purity of the liquid. So in this case, we are considering that our water is 100% pure, so we take it as 1, and that's how we get 55.5. Same way you can calculate for HCl, H2SO4, or for that matter any liquid, and you can find out the specific gravity of that particular liquid from the bottle of that solution, or just Google it, and the purity is on the bottle of that solution. So this is the way we calculate the molarity of a solution. Now the next term is this, if we rearrange, and this next term is called as Kw. Now, if we find out what is the conductivity of pure water through experiments, it is 1.8 into 10 to power minus 16. So the kW of water is 55.5 into this number, and which comes to 10 to the power minus 14. So the kW of water, which means the concentration of H plus and OH minus, is going to be 10 to power minus 14, which means if we take individually, then we can find that H plus or OH minus is 10 to power minus 7 molar. So this is the concentration of hydrogen ion or hydroxyl ion in the water if they ionize. Now to simplify this, we take a log. Yeah, I know, as a biologist, this will freak you out, that log. Yes, uh, but it is a mathematical operator which is actually there to simplify the large numbers. Like for example, that 10 to power minus 7, if you take a log of it, it comes to 7. Sorry, negative log of it is 7. And that is the concept. So if we have a normal scale, like it would be like this. So there is a 1, then there will be a 10, then there will be 100, and there would be very far away, there would be 1,000. Now this scale will be complicated. To simplify this, if you make a log scale, in log scale the same thing can be represented as 1, 2, 3 and 4. Log to the base 10 is 1, 100 is 2, 1,000 is 3, and 10,000 would be 4. And so in this way we can simplify things, and that's why we take a log. So the pH, the concept of pH is simple, that it is log of 1 by hydrogen ion concentration, and same log is something like this, that if it is 1 by H plus, it can become H plus if we add this negative sign. So pH is basically a negative log of hydrogen ion concentration. So why we are taking log here? Not to complicate things, but to simplify, right? To simplify our scale. So instead of using large numbers like 10 to power minus 5, minus 6, we can use a simple number like 1, 2, 3, 4, 5, 6. So if we see the log scale, what is the maximum concentration of H plus is possible from the last equation? It is 10 to power minus 14, right? When there is no hydroxyl ion and there is only H plus ion, the only possible thing is that 10 to power minus 14, right? So this would be the minimum concentration of H plus. And what is the possible maximum concentration is this one, 0.1 molar. Okay, technically there will be no pH 0. Same way, if we see that the concept of POH is same as it is log of 1 by hydroxyl ions, which is this 1 by OH can be presented as minus log OH minus, right? So things are very simple. So if I have a concentration, for example, if there is an HCl, okay, let's take an example that it is 0.01 molar, which means the concentration is 10 to power say minus 2 molar, where HCl can be dissociated into H plus and Cl minus. So what would be the concentration of H plus? 10 to the power minus 2. So what would be the pH? Yes, the pH would be 2. It's the negative log of it. Remember the scale I talked in this session? Okay, so let's see this. And if this concentrations, for example, same HCl, if it is 10 to the power minus 8 molar. Now what would be the pH of HCl? So this time the pH of HCl would be something in between 6 to 7. Now what happened? Here we're talking about the hydrogen ion concentration. Okay, and HCl is a strong acid. Now when we talk about strong acid, it has some hydrogen ion concentration. For example, here in this case it would be, say, 10 to the power minus 8. And what would be the hydrogen ion concentration in the pure water? Is 10 to the power minus 7, right? So even if water ionizes, pure water ionizes, there would be this amount of H plus ion in the system, right? So the pH of pure water would be 7, right? And we are adding acid, but the acid concentration is very low. So as this concentration keeps on decreasing, for example it goes on 10 to the power minus 8, minus 9, minus 10, so the pH will be range between 6 to 7 and trying to reach 7, tending towards 7, but never reach 7 because HCl is an acid. Okay, now to understand this better, we need to understand the concept of weak acid, bases, and the strong acid. So one of this is acetic acid. Okay, so this acetic acid can be dissociated into H plus and CH3CO minus. Now we are calling this as a weak acid. What does that mean? Now weak acid is something which is an acid when there is a base, but if there is an acid, for example if I make a solution of acetic acid and HCl, okay, so if I add HCl into the medium, what will happen, that this will start behaving like a base. To understand what is acid and base, we will simplify it as the one which provide H plus is an acid and the one which is accepting H plus is a base. So this CH3COH is releasing a H plus, it is an acid, but this CH3COO minus is accepting an H to become CH3COH, and that's why it's a base. So the same thing is acting as an acid and a base. This we call it as conjugate acid base. Which means if the pH is low, how pH is low? Because we added HCl. So if the pH is low, always this will behave like a base and it will accept H plus and become CH3COH. Whereas if the pH is low, in that case this will donate it H and C and it will dissociate into CH3CO minus. Again the concept is same, the K equilibrium concept. Remember, the concentration at the equilibrium, the concentration of this CH3COOH will be equal to H plus and CH3CO minus. To simplify this, what we can write it in the form of HA, which is dissociated into H plus and A minus, and we can put up in the K equilibrium concept like we did it for water, and this gives us something called as Ka, dissociation constant. So at equilibrium both of these will dissociate. So there will be, say in equilibrium, 50% of this would be acetic acid, 50% of this would be CH3CO minus and H, right? So at an equilibrium both of them would be of equal number. Now to simplify this number, so for example the concentration would be say 10 to power minus 5, and to simplify like we did it for the hydrogen ion concentration, if we take a log of this we get pKa, we get this pKa, which is nothing but minus log of K. What is K? K is a dissociation constant which is basically the ionized, if a reaction which is ionization, K equilibrium. So if any reaction which is in equilibrium, we can represent an ionization product as a dissociation constant, and since this number would be big like 10 to power minus 6 minus 5, we simplify it by taking a negative log and make it as pKa. Now let's try to understand this with this example. So the acetic acid, so if I say the pKa of acetic acid is 4.7, what does it mean? It means that at this pH, which is 4.7, we have equal number of CH3COOH and CH3CO minus, right? Because Ka of acetic acid, look at this one, it is 1.74 into 10 to power minus 5. To simplify it, what we can do is we can take a log of it, and what logs come as pKa, which is 4.76. Now what does this 4.76 mean on a pH scale? It means that at this particular pH this acetic acid will be in equilibrium. Same thing happens for the ammonium ion, right? This is ammonium ion, which is 5, the K is 5.62 into 10 to power minus 10. So this is a large number. So what we do is we take a negative log of Ka and we get a pKa, which is 9.25. So if I ask you that at pH 9.5, what would be the concentration of these two? So the concentration of ammonium NH4 plus and NH3 is 50% of 50-50 equal concentration of this. Now if I ask you what would be the concentration at pH 8, right? This is an equilibrium where they are in equal. So if I move towards my left, this component will increase, and if I move right side, this component will increase. Now same thing will happen with this. So if the pH is less than 4, this ion would be more at pH 4, whereas at pH 8 this ion will be more in number, and at 4.76 pH both of them would be 50-50 in equilibrium, right? I hope you're understanding it little better. And so we just see some of the acid which are diprotic, like NH2CO3. This will dissociate into HCO3 minus and H plus, and also it will dissociate again from HCO3 minus to CO2 minus and H plus. So two time dissociation will take place, and so there will be two pKa's, right? So one pK is at 3.77 and the another pK is 10.2. So if I ask you that at pH say 7, at pH 7, which ion will be in the highest concentration? Think about it. Yes, so remember the concept that if it is more than 3.7, HCO3 will be more. If it is less, then H2CO3 would be more. Similarly, if it is less than 10.2, HCO3 minus would be more. If it is more than 10.2, then CO2 minus would be more. So the pH 7 is basically average of 10.2 plus 3.7 divided by 2, that comes to 7 roughly, and which means that this HCO3 would be maximum, because this is the particular concentration where this would be maximum, right? Now let's see this in terms of glycine. So our next example is glycine. So here this also behave like a diprotic acid. There are two H plus releases. Okay, one H plus is released from COOH. Remember glycine structure? If you want to see how to memorize structure of amino acid and their properties, please see my video for this, which was there in last session. So here one H plus is released, okay, and the other H plus is released here with the ammonia, right? If you see, this glycine is a part of acetic acid, right? And this ammonium ion NH3 plus is something like the ammonium ion dissociation we have seen, right? So there would be two dissociation, two groups, two dissociation, and if you see that um, first dissociation is at 2.34. So if I ask you that the pH is less than 2.2, what would be the charge on glycine? The charge on glycine would be a positive charge, right? And what would be the charge on glycine if pH is more than 10? A negative charge, right? Why? Because after, if we move towards right, it would be more of these negative ions. If we move left, there would be more of this ion. So what would be the charge on glycine at 9.6 plus 2.34 rough divided by 2, roughly it will be coming to 6. So say if I ask you what would be the charge on glycine at pH 6, Using this concept, you can average it. So most of the ions which would be available would be NH3 plus and CO minus from both the side, which means plus minus is 1 plus and minus 1 equals to 0. And so this would be the pi of glycine. We'll see pi just in the next session, but here I want you to understand that as pH varies, what would be the concentration on this. Now you can pause this video and look at it for this phosphoric acid, which dissociate 3 times, like from H3PO4 to H2PO4 minus, then H2PO4 minus to HPO2 minus, and then further to from HPO2 minus to HPO3 minus. Now 3 dissociation will have 3 pKs. Okay, and we can understand at what pH which concentration which ion is more, and that's what is I want to make you understand, that if this particular pH is there, then which particular ion will be more and which particular will be less, and equilibrium which would be the ion which is in right concentration. Okay, now let's see a titration curve. What do I mean by this ion concentration and the other ion concentration, how it is relevant in biology? So first idea we get it from acetic acid itself. So we'll use this one to understand the concept better. So we know that the pKa of acetic acid is 4.76. So if I ask you at pH 2 which ion would be maximum, it is CH3COOH. Now which ion would be maximum at a pH say 6? After 6 it would be acetate, like CH3CO minus. Now what does that mean? It means that if you take an acetic acid solution which has a pH less than 2, then all these ions would be acetic acid. And then when you slowly titrate this with a hydroxyl ion concentration like 0.1, 0.2, 0.3 and so on, these many equivalents of the concentration, and when we talk about concentration we talk in terms of molarity, okay, which we discussed about the water, remember. So moles, gram moles per liter. So as we do adding this, now it doesn't go straight from 2 to 6, but what happened that first when you add it will increase and then it will slowly increasing, which means at this particular point in this particular range you added so much of acid but the change in pH was very less. This is called as buffering region. So for acetic acid it is 5.76, and similarly a region in which it is from, so for acetic acid it is a region between 3.76 to 5.76. okay, now here if I at this particular point, at this particular pKa, the concentration of both CH3COOH and CH3CO minus is almost equal. So if you add more OH, there would be more acetate. If you add less of OH, there would be more of CH3COOH, right? So from this we can understand that how this buffering capacity works. So basically the pKa, which we can see experimentally also, the pKa, if I ask you find out pKa, how would you do it, is you will make a plot, and the midpoint of this plot would be the pKa, right? The midpoint of the plot means what? Where CH3COOH is equal to CH3COO minus. So if we see experimentally what we have learned uh, theoretically, what we understand is what is actually pKa, right? pKa is that pH at which both the ionized ions are in equilibrium. That's all I want to explain. The one more thing which I want to add is, if the hydroxyl ion concentration is more, it will move towards right. If hydroxyl ion concentration is less, it would move towards left. Okay. Now let's see all these examples together, like acetic acid, H2PO4 dissociation, and ammonium ion. So at pH 2, right, you keep on adding hydroxyl ions, and this kind of curve you will get. You will get a pK like here for acetic acids, the midpoint pK for H2PO4, HPO4, or ammonium ion like NH4 plus and NH3. They all would be the middle. And here you need to understand that here we started titration from 7. Scale is from 7 to 12, right? So what is the buffering region? From 8 to 10.25. The middle of this buffering region is what? The pKa. Similarly, if we see for H2PO4, it starts from 4, it goes till 9, and the buffering region is this one, 7.86 to 5.86, and the middle of this, the midpoint is 6.86. Similarly, if we see acetate, this is the buffering region, 5.76 to 3.76, and what we have is this midpoint. Now from this you can understand that this could be, we can plot it for H3PO4 for example, right? If we make it for H3PO4 minus, here somewhere it would be H2PO4 minus. How did I get this number? From this point, because this point is, it will be maximum, and we would have got a similar curve like this for that, and this would have been the midpoint. I hope you have understood that how acid base work, how the buffering capacity work, what is pH, what is pKa in this system. If we have understood, then it is very simple to understand what is Henderson Hasselbalch equation. So like we did in the last section, where we use this dissociation constant which has H plus and A minus, which was in equilibrium with HA, we can easily represent it in terms of H plus, K, HA and A minus, right? How do we get this? We get this by just rearranging the above equation, and then we took negative log of both the side, right? Now what does negative log mean? Why did we use log? Not to complicate but to simplify the number like hydrogen ion concentration would be in range of 10 to power minus 3 or minus 4. Dissociation would be in similar way, and so to reduce this complicated number into simplified number like 1 2 3 4, we use negative log. And if we take a negative log, we know that negative log of hydrogen ion concentration is pH, negative log of hydrogen ion concentration is pKa, and so we get this equation, right? And remember that if you take a negative, this thing get reverse, like 1 by hydrogen ion concentration, so log 1 by hydrogen ion concentration, you remember this, we can represent it as negative log hydrogen ion concentration. Okay, negative log hydrogen concentration. Same way, if we can do this for minus log Ha, we can just reverse, just invert this, and we can get it plus instead of minus. So pH is equal to pK plus log of A minus divided by Ha concentration. And this is our Henderson Hasselbalch equation, which tells us that pH will be equal to pKa plus log proton acceptor and proton donor. This is a kind of acid, and this is a kind of base in the conjugate acid base system. Before closing this session, we would like to see what actually does that mean in the cellular system, that what does this weak acid and base do. So this is the structure. Can you tell me what is the structure? This one is an amino acid which is histidine. Yes, so histidine has a side chain which has a pKa of 6. Okay, so the side chain of histidine is pH 6, and we all know that the protein which contain histidine can effectively buffer at physiological pH. What is physiological pH? 7.35 to 7.45. How it can buffer it better? Because it has a pKa of 6, which is close to the physiological pH. I hope you have understood this concept better, and then we can move to understand the titration curves of amino acid, how PIs can be determined, and what do they actually mean in the biological system. Stay tuned. Have a wonderful time. Thank you.